ATLS, Agentic or Latent Visual Reasoning. One word is enough for both.
Yeah, that's from researchers at Meta AI and the Chinese University of Hong Kong.
Right, so here is the 1-minute rapid-fire summary for you, just in case you're prepping for a meeting right now.
Multimodal models, they really struggle with intermediate visual reasoning.
Like zooming in on a blurry image or maybe cropping a specific object before trying to answer a question.
Exactly. And current fixes are, well, they're essentially broken for engineers. They're either way too slow because the model has to write Python code to call external tools.
Or they completely break the model's architecture by generating pixel-level images.
Right, or they rely on continuous latent embeddings that absolutely ruin parallel training on GPUs.
So the ATLA's core breakthrough completely bypasses those dead ends.
It does. The framework solves the problem by adding just 5 simple, discrete functional tokens to the model's standard text vocabulary.
Words like shape or line.
Yeah, and these act as internalized visual operations. So by training this with a novel reinforcement learning objective called Latent-Anchored GRPO, or LA-GRPO.
LA-GRPO, right.
Yeah, they prevent these rare functional tokens from getting drowned out by normal text tokens during training. The model literally learns to look at and manipulate specific parts of an image just by predicting the next text token in a sequence.
And the headline result you need to know, ATLS more than doubles performance on the highly challenging BLINK benchmark, jumping from 22.8% to 51.3% accuracy.
Which is massive.
It is. And it does this while cutting inference latency from nearly 19 seconds down to just 3.8 seconds compared to agentic baselines.
It's a huge leap.
Welcome to AI Paper Podcast. This is the YouTube series where we break down the latest AI and tech papers for researchers and ML engineers.
Today we are taking you on a deep dive into this incredibly elegant paper.
We're going to break down the architecture, the training pipeline, and exactly why this specific approach matters so much if you are building or deploying vision language models today.
I mean, it represents a massive shift in how we think about intermediate reasoning steps in AI. For a long time, we've been trying to force models to reason visually, either the exact way humans do by rendering images or by giving them clunky external tools.
Right.
But this paper asks a radically different, almost painfully simple question. What if the model just needs a slightly expanded text vocabulary to do its visual thinking internally?
Okay, let's unpack this. Because to really appreciate the ATLAS solution, we first need to understand the absolute headache that is the current state of multimodal reasoning.
Oh, it is a massive headache.
We've established that visual reasoning is broken in current VLMs. When a model needs to do something complex, it struggles. So ML engineers have basically come up with 3 paradigms to try and fix this.
And all 3 create friction.
Exactly. Paradigm 1 is building unified models. This is where the model generates actual pixel-level images during its reasoning process.
Which is an absolute nightmare computationally.
Yeah.
You are forcing the model to decode and re-encode full images just to say, like, I drew a line here to separate these 2 objects.
Wow, yeah.
It requires massive, non-trivial architectural changes to your framework.
Yeah.
Often, you have to pre-train the entire model from scratch to handle this continuous image generation loop.
So if you're an engineer trying to build a snappy, responsive application, rendering intermediate pixels is just not scalable for quick reasoning tasks.
Not at all.
That latency problem is exactly what led to paradigm 2, agentic methods. This is where you treat the vision language model as a high-level controller.
Right. So instead of drawing the image itself, it writes a Python script.
Yeah, it outputs something like, let me write some code to call an external cropping tool or drawing function.
To give you an analogy, it's like a master chef having to physically leave the kitchen, walk down the hall, read a recipe book, and then walk all the way back every single time they need to chop a carrot.
That is a perfect way to put it. And that context-switching latency is a killer for production pipelines.
It really is. The model has to formulate verbose Python code, send it to an external execution environment, wait for the external tool to run.
To process the output and ingest the result back into its context window.
Exactly. When it takes an 18-second wait time just to answer a basic visual question, your real-time application is essentially unusable.
Which brings us to the third attempted fix, paradigm 3, latent methods.
Yes.
Instead of dealing with pixels or writing slow Python code, the model reasons in continuous hidden embeddings.
So it's like our chef is now thinking in a telepathic abstract language.
But from an ML engineering perspective, you've mentioned before that this completely breaks the standard kitchen workflow.
It does.
Why is latent reasoning such a poison pill for training pipelines?
Well, what you have to understand about modern large language model training is that its incredible scalability comes from autoregressive parallelization. Normally, models are trained to predict the next word across an entire sequence simultaneously, and that's the beauty of it.
Right, because you use teacher forcing, feed the whole ground truth sequence in, and compute the loss for all tokens at once across your massive GPU cluster.
Precisely. Because every step is discrete and known during training, you don't have to wait for the model to guess the third word before grading the fourth word.
Okay, so what goes wrong with latents?
The moment you introduce continuous latent reasoning, you introduce recurrent latent dependencies. The next hidden state depends entirely on the computation of the previous hidden state, which is continuous and dynamic, not neatly tokenized.
Oh, I see. So step 2 suddenly has to wait for step 1 to finish computing.
Exactly. You've just turned your massive, highly parallel GPU cluster into a slow, step-by-step traffic jam. It destroys your training efficiency and severely limits how well you can scale the model because you are bottlenecked by recurrent operations.
So, if pixels are too heavy, code is too slow, and continuous latents break our training loops, how do we get the model to see intermediate steps without destroying our architecture?
What's fascinating here is how the ATLA's researchers looked at that exact bottleneck and decided to hide their solution in plain sight.
I love this part.
They took a standard model, specifically they used Quinn 2.5 VL7B, and they didn't touch the underlying architecture at all.
No new image decoding heads.
None. No external Python execution environments, no continuous latent states. They just added 5 discrete functional tokens directly into the standard text tokenizer vocabulary.
Just 5 words. Let me list these tokens for you so you can visualize what we are talking about. Token 1 is shape, which the model uses for localizing objects, drawing shapes, or cropping.
Very useful.
Token 2 is line, for drawing auxiliary lines or connecting points. Token 3 is arrow, for pointing to specific regions. Token 4 is manip, for spatial manipulation or zooming. And token 5 is filter, for visual enhancement, like boosting the contrast on a blurry texted image.
Oh, wait, hold on. I have to push back here.
Okay, go ahead.
You're telling me they literally just typed 5 new vocabulary words into the standard text dictionary, and suddenly the model knows how to visually manipulate an image?
Pretty much, yeah.
How is that physically possible without changing the vision architecture? There is no pixel-level visual supervision happening. How does predicting a piece of text that says shape result in a visual operation? It sounds like magic, but it's just brilliant ML design. These functional tokens are optimized strictly with standard cross-entropy loss over token sequences.
Okay.
Because they sit inside the same vocabulary as normal words like, apple or there. Therefore, the model learns from the surrounding text context when and how to invoke them.
Because the model already has a vision encoder mapping visual features into the shared latent space.
Exactly. So the text and the vision are already talking to each other.
Right.
So if the reasoning trajectory generated by the model says, I will first add an auxiliary line to the diagram to find the height, the very next predicted token naturally becomes line.
Wow.
Because learning to predict that specific text token minimizes the loss, the model's internal attention mechanisms are forced to associate that textual intent with the corresponding visual features in the image.
So it learns that predicting line in the context of a geometry problem requires attending to specific spatial coordinates in the visual embeddings.
Exactly. It builds an internalized visual operation entirely through text prediction.
That is wild. And because it's just predicting the next discrete text token, it remains fully compatible with standard supervised fine-tuning and reinforcement learning.
Yep. You don't have to change a single line of your standard autoregressive training architecture. You're just adding 5 new words to the dictionary.
It elegantly bypasses all 3 paradigms. No pixel decoding, no external code execution, and no recurrent latent traffic jams. Just standard next token prediction.
But, getting a model to actually use those 5 tokens effectively requires a very specific recipe.
Right. You can't just drop line into the vocabulary and expect the model to start solving complex geometry without some heavy lifting in the training pipeline.
No, definitely not. And this is where the paper provides a masterclass for ML practitioners on how to train a model to utilize these custom tokens. You need to provide the model with a reliable cold start.
Which means?
The researchers implemented a 2-stage training recipe. Stage 1 is supervised fine-tuning. or SFT, using a brand new dataset they curated called ATLAS-178K.
The way they built that dataset solves a massive problem. They started with an existing dataset called V interaction 400K.
Right.
That dataset is basically a bunch of visual reasoning problems paired with Python code that draws lines or crops images to solve the problems.
The researchers parsed out that raw code and mapped those coding actions directly to their new functional tokens.
But reading raw code translation is, well, it's highly mechanical. It doesn't mimic human reasoning. So they used Gemini 2.5 Pro to polish the reasoning trajectories into natural text.
Translating raw code into natural language reasoning trajectories is crucial here. By having Gemini rewrite it, the tool use becomes directly integrated into the LLM's natural thought process.
Ah, I see.
The SFT data reads organically, seamlessly weaving tokens like filter right into a chain of thought reasoning path. This SFT sage teaches the model the basic syntax.
It teaches it that when it encounters a tiny, unreadable font, it should output the shape token to localize it.
Exactly. But SFT alone is essentially just mimicking the training data.
Right. To get the model to truly reason, explore, and optimize for the correct final answer, you need stage 2. Reinforcement learning.
And here, they utilize GRPO, Group Relative Policy Optimization, which has become the gold standard recently.
Here's where it gets really interesting. When they started running standard GRPO on this model, they slammed into a massive statistical roadblock.
They encountered a severe issue they termed gradient dilution. Let's look at the raw numbers from the model's reasoning trajectories.
Okay, lay it on me.
In an average response generated by ATLA, the sequence is about 203 tokens long. Out of those 203 tokens, only about 4.8 of them are functional tokens.
Wait, really? That low?
Yeah. That means the crucial visual operations make up just 2.3% of the entire generated sequence.
Wow. To give you a metaphor for how bad that is, imagine grading a 200-word math essay where only 4 words actually matter for solving the final equation.
That's a great comparison.
In standard GRPO, the learning signal, the teacher's red pen, is distributed across all the tokens. The teacher is bleeding red ink all over the grammar, the formatting, and the transition sentences of the other 196 words.
Right.
As a result, the student completely misses the specific feedback on the 4 vital words that actually solve the math problem. The signal you care about is entirely drowned out by the noise.
Exactly. When the gradient is diluted like that across standard text tokens, the model's learning becomes highly unstable. It either underuses the functional tokens because it isn't rewarded enough for them, or it uses them randomly.
So what did they do?
To fix this, the researchers couldn't use standard GRPO. They developed Latent-Anchored GRPO, or LA-GRPO.
And how does that actually change the mechanics of the training?
They augmented the standard GRPO objective with a statically weighted token-level auxiliary loss. Crucially, this auxiliary loss is anchored specifically to the exact index positions of the functional tokens.
So by using a static weight, they are essentially pinning a multiplier to those specific shape or line tokens.
Correct.
When the model generates a sequence, the training algorithm scans through, finds those exact tokens, and when it does a backward pass to update the model's weights, the loss signal spikes massively at those specific coordinates.
Exactly that. It forces the algorithm to pay disproportionate attention to the visual reasoning steps.
Oh, that makes sense.
It ensures those specific neural pathways, getting the model to utilize the functional tokens, receive strong, consistent gradient updates, cutting right through the noise of the standard text generation.
But if you amplify the reward signal on those specific tokens that much, how do you make sure the model doesn't just learn the wrong lessons? I mean, if it knows a functional token triggers a massive gradient update, won't it just abuse them?
That is the perpetual danger of reinforcement learning. You have to be incredibly careful with your RL reward design.
So what did they do?
They used a diverse reward ensemble. You get a reward for correctness. Did you output the correct final answer? You get rewards for formatting and penalties for excessive length to keep the reasoning concise.
Right.
But the most vital component they added to the reward model was a spam penalty.
I have to say, the ablation study on this in the paper is hilarious. They tested what happens if you remove that specific spam penalty.
Oh yeah, it gets wild.
Without it, the model immediately engaged in severe reward hacking. It figured out that functional tokens were associated with positive updates, so it just started generating up to 18.7 functional tokens per sequence.
You just spammed them.
It was basically screaming shape, shape, shape over and over again to accumulate points without actually doing any logical reasoning.
Right, so the spam penalty explicitly bounds that behavior, forcing the model to only invoke the tokens when they genuinely support reaching the correct final answer.
So if we connect this to the bigger picture, what does this actually achieve? The results on the BLINK benchmark are stunning.
They really are.
Yeah.
BLINK is notoriously difficult for multimodal models because it requires deep, multi-step visual perception, not just high-level image captioning.
Exactly. The base model they started with, Qwen 2.5 VL, scored 22.8%.
Which is pretty typical.
But with just the supervised fine-tuning stage, ATLS jumped to 46.0%.
Huge jump.
And when they applied the LA-GRPO reinforcement learning with that targeted multiplier, it hit 51.3%.
That is more than doubling the base model's performance on a brutal benchmark without adding a single parameter to the architecture.
To really help you visualize what this looks like in practice, the paper provides some incredible concrete examples of the model in action.
Oh, I love these.
There's one where the model is given a photo of a snowboarder climbing up a snowy peak, and it's asked a question about the text written on the bottom of the snowboard. The text is tiny, it's upside down, and it's faded against the snow.
A standard model would just guess based on the context of snowboarding or maybe just hallucinate a brand name.
Right. But ATLAS outputs a genuine internalized thought process. It says, the text is faint, I need to focus on the logo area.
And it outputs the shape token to mentally localize the board.
Then it says, it's still hard to read due to lighting. I will apply a filter to enhance the local contrast, and it outputs the manip token.
And after doing that internally, it successfully reads the brand name Jones and answers the question correctly.
There's also a great spatial reasoning example, an image of a cat sitting inside looking out a glass door with a car parked outside in the background. The question is simply, is the car beneath the cat?
And ATLA outputs, I should first localize the cat clearly, uses the shape token, and then correctly determines the car is in the upper left of the background, not beneath it.
It even works for math. Given a trapezoid where it needs the height, it outputs the line token to mentally draw the perpendicular height before calculating the area.
But what's truly remarkable, I mean, the real aha moment of this paper, is that we can prove the model isn't just faking it.
Right, it isn't just parroting the text it learned during SFT.
Exactly. The researchers visualized the attention maps of the model during these reasoning steps.
I want to slow down here because this is the closest thing to mind reading and AI we have. You're saying that when the text generator prints the word shape, we can look under the hood at the vision encoder's attention heads, and they are physically lighting up over the exact pixels of the cat.
That is exactly what is happening. It is bridging text and vision perfectly. When the model predicts the shape token to localize the cat, the attention weights inside the neural network are firing hot directly over the exact pixels of the cat in the image.
That's incredible.
When it outputs line for the trapezoid, the attention map shows a glowing line drawn exactly where the height should be. It is definitive mathematical proof that the token isn't just a textual marker.
It is genuinely integrated into the visual reasoning process. It is actively looking at the right thing.
Yeah.
So we have this beautiful internal attention map, but honestly, none of that matters to an ML engineer if it takes 20 seconds to run. The whole reason agentic models failed was latency. Did ATLS actually solve the speed problem?
Oh, absolutely. The efficiency wins are exactly what will make practitioners adopt this. Compared to a state-of-the-art agentic model like vThinker, which relies on Python code generation, ATLAS reduces the latency from 18.83 seconds down to just 3.80 seconds.
Wow, that is nearly a 5x speed up.
And what about memory? Because you aren't holding heavy external environments or execution loops in memory.
Right.
It cuts peak memory usage almost in half, dropping from 2.55 gigabytes down to 1.43 gigabytes, because every complex visual operation is compressed into a single discrete token.
It doesn't need to generate 50 tokens of verbose Python code to draw a line. It just says line.
Exactly. It is incredibly compact and perfectly suited for fast, parallel autoregressive generation.
So what does this all mean? If you are building multimodal applications today, ATLAs prove a fundamental shift in how we handle complex reasoning.
You don't need clunky external agents.
You don't need to rebuild your model architecture to generate pixel-level images.
And you definitely don't need to rely on unscalable, continuous latent embeddings that turn your GPU clusters into a traffic jam.
One discrete word, a functional token like line, trained smartly with Latent-Anchored GRPO to overcome gradient dilution, is enough to unlock complex visual reasoning.
This raises an important question, though. Something for everyone building these models to think about.
Okay, what is it?
The researchers here predefined these 5 functional tokens. They decided beforehand that the model needed a line token, a shape token, a filter token.
Right.
But we've just proven that a model can fully internalize complex visual operations into standard discrete text tokens through reinforcement learning.
Oh, I see where you're going with this.
So what happens when we remove the training wheels? What happens when we let the RL algorithm invent its own functional tokens from scratch?
Wow.
Could future vision language models develop a completely discrete, internalized vocabulary for visual logic, an alien language of thought that human beings can't even conceptualize, yet perfectly and efficiently solves the task?
Now, that is a thought to leave you with. An AI developing its own discrete visual vocabulary. Thank you for joining us for this deep dive into the ATLA's paper on AI Paper Podcasts.
We highly recommend thinking about how you might be able to leverage discrete functional tokens and anchored GRPO in your own ML pipelines.
Until next time, keep exploring.